So can we get started? Yeah. So good afternoon, everyone. Thank you so much for coming today. I'm really delighted to be here today to see you all and to witness the progression of Mirza into a soon-to-be doctor. Today I'll be talking about my research on digital twins and particularly the application of intelligent transportation systems. I know that holiday starts very soon, and I really am grateful for you to showing up this afternoon. So the title of my topic today is Digital Twins for Decision-Making in Complex Systems, and particularly about intelligent transportation systems. So there are two main things in the topic, digital twins, and I'll first want to stop and talk about that and try to frame it, because defining digital twins is almost impossible. And rather than defining digital twins, I'll talk about different levels of digital twins. And sometimes people talk about digital twins as if there's something new. They're not new. We've done modeling forever. We've always done modeling. We did it differently. And the level one, which you see there on the right side, is where we tried to summarize a phenomenon and a model, and that model was analytical. And it could be anything that you wanted to model. But to do that, you had to simplify it. You had to make it general and not precise. The level two digital twin is when we started having these connected devices, IoT devices. And with IoT devices, we have access to real-time data. And this is where we have that component of bringing real-time data into the model. And that model goes away from just being a general model into reflecting that particular environment based on particular data. So this is the data-driven modeling. And this is the level two. And you have many examples of those level two. The level three modeling is where we start having the two-way information. So instead of just taking data from the physical environment to have a better model in the virtual world, then we start bringing back the intelligence, the insights from the virtual world into the actual physical world, and making something there, making a change, making intelligent decisions based on that. But in the level three, we always have the man in the middle, or the person in the middle, which takes that insight, looks into it, decides whether it's be implemented or not, and then this is what gets implemented. The latest level is the level four, is the autonomous decision. And this is where we have two-way communication in real time, and it's completely autonomous. And this is where we can really do the best job. But of course, it comes with risks. If you were to apply that to the transportation sector, I don't know if anyone is familiar with this model. So this is a very old model, 1935. Shields tried to model how traffic flow is affected by speed and by occupancy. Speed is the speed of vehicles on the road. Occupancy is the number of cars along that road, or per kilometer squared. And he decided that that equation tells us for the flip side, we have kilometers per hour. This is the speed. The occupancy is vehicles per kilometer. We multiply those, you have then kilometers vehicle per hour, which is the flow. And he said, well, in order to maximize the flow, we can't have the maximum speed and we can't have the maximum density. We need to have something in between. And this is the best flow is when we have medium speed, and the best flow is when we have medium density. And that's an equation. And that equation was used to design traffic, to design roads, to understand the size of the road, and to manage the flow of traffic. And it worked well. And then we moved on to the level two. And this is data taken from California. So I don't know if you're familiar with this site. Caltran gives you real-time access to data along most of the roads in California. It's quite interesting to check this data and to see how it was affected by the fires last year. And what you have now is you have the sensor data, we have the real-time data, and you try to compare the IoT data, the level 2 model, the analytical model. They do look almost the same, but they're not exactly the same, of course. So real-time data does not follow that linear shape exactly, but it has the same trend and the same thing when we compare the when we compare the speed, the actual speed based on the IoT data to the analytical model and vice versa. So what the level 2 tells us is we move away from this one equation represents all to a model that is actually representative of this particular road. We can make it more personalized, more precise. And that's very good because then when we want to make decisions based on this data, we know that that is representative of this particular road or stretch, physical environment. And then the third level is where we want to control the physical world based on the insights that we have in the virtual world. So we get all of this data, we model it in the digital twin environment, we come up with optimization intelligence. It could be rerouting a certain robot, it could be controlling the traffic lights in order to control the flow of vehicles. And that decision is still going through a person in the middle. It's not automatically blindly applied. And then the last one, and this is ChatGPT that created this image for me. I gave it this description and it came back with this image, and I like the image. So this is what we're now calling the agentic digital twin. So we're moving away from digital twins that we talked about before into agentic digital twin, because with agentic AI, you have a potential to do so much with digital twin. And that so much is really impressive because you move away from that distinction of physical and virtual world, and they become a hybrid coexisting entity together, where the virtual world affects the physical world, and the physical world affects the hybrid world. And this is a very good paper recently published, still in archive. I don't know if you know David White. David White is he's leading the digital twin network plus in the UK. Jason is from Fujitsu, and Christopher Burr is from Newcastle, and they're all working on digital twinning. This is the most recent article, and it's really interesting because it goes through the capabilities of digital twinning and talks about these three different axes. But what is important from a transportation point of view is that you don't have roads anymore as physical routes. Now they become a dynamic flow of resources. Vehicles are no longer vehicles to carry people around or goods. No, they become a network of computational nodes that are moving. Trips become statistical entities instead of A to B, deterministic entities. And with that level of digital twinning, we can do a lot. We're not there yet. I don't think this is yet possible. This is something that will happen in the future. And it carries a lot of potential, really. But it also carries lots of challenges. So that's a very brief description of these different levels of digital twins. You hear the term everywhere, they need for everything, and all of them can be digital twins. It's not a very well-defined concept. It's an evolving concept. The other keyword in the, or key expression in the title is intelligent transportation systems. So I just wanted to, again, take a minute to talk about that. An intelligent transportation system is one that takes a normal transportation system, which is not so intelligent, and we start adding components to it. We add information, and this is often using sensing technology. So with sensing technology, with IoT devices, we have access to real-time information. When you bring information, you need communication technology, and when you bring them together, then you have access to real-time data anywhere, anytime. And this is how you can start coming up with intelligent applications. So intelligent transportation systems are about improving the safety, the sustainability, reliability, energy efficiency, the quality of transportation. So these are the applications. This is the business value that I want to create with intelligent transportation systems. And to do that, I need information, I need communication, and of course, I need AI. I need AI, I need digital twinnings, I need generative AI, LLMs, blockchains, quantum computing at one point. All types of digital technologies are tools to enable intelligent transportation systems. Why do I care about intelligent transportation systems? I'm personally very much interested in the impact of transportation on climate change and on public health. We're all aware of the rising temperatures globally, and they're alarming. They're creating extreme weather conditions. 99% of us people living in cities, probably not you here, because this is just beautiful and so green. But the rest of us living in cities, we are breathing polluted air all the time. 99% of us are. Pollution causes 6.7 million premature deaths worldwide. A lot of it is because of transport-related air pollution. And the most nasty pollutants are the particulate matters. So these are the tiny components in air, in the air pollution, that affects our respiratory system, of course, our cardiovascular system, but also our brain, our cognitive function. It affects pregnancy outcomes. It affects mental health. All of that is affected by pollution. In the UK alone, transportation, particularly road transportation, is responsible for the highest nitrogen oxides because of road transport, and a major contributor to PMs, the particulate matter. So that's why ITS, that's why I'm interested in ITS. And that's why I'm interested in particularly active travel. Active travel is a form of transport where you don't need a vehicle. You don't need a motorized vehicle. It could be cycling, it could be riding a scooter, it could be walking, jogging, all of that is called active travel. And a push in the UK is to have people do the last mile of their journey using active travel. Don't drive, don't use the bus, don't use the underground, walk, cycle. We want to do that, but there are lots of challenges. And I will talk about two use cases that we do in my research, where we use digital twinning to improve active travel. The first one is about pedestrian intent prediction. And in particular, the intent that we want to predict is whether a pedestrian will cross the street or not. Why do I care about that? I've got this complex system of road transport. The road is shared by cars, it's shared by bicycles, by people running, jogging, senior citizens, children. Most of these have some sort of IoT devices, connected devices, information is available through different protocols. I can create a model in the digital twin space based on that physical environment. And that model is not just to have a fancy visualization, it's to make intelligent decisions. Can I predict if a pedestrian is going to cross the street? And can I do that fast enough and accurate enough, control the traffic signal and turn it to red if I know that someone's going to cross the streets? Or can I do that to control the autonomous vehicles on the roads? I don't know what's the situation in Ireland, but in the UK, we will have autonomous vehicles starting this year, 2026. We can start booking our autonomous rides with Uber. We need to make sure that these vehicles immediately stop if there's a pedestrian who will cross the street. And that's not easy. That's not easy at all. So there's lots of research out there that looks into this particular. And not in a digital twin, environments just to find an algorithm that can predict the event of pedestrians. You can look at mass accuracies, but all of them are very complex algorithms. It takes a long time to predict, too long to prevent a collision, too long when I compare the computation requirements of these algorithms that you see there. Let me get my pen. The computation algorithm of the complexity of these algorithms, when I compare that to the capabilities of roadside units, these are the edge servers on the road that get all the data and compile this data to come up with the prediction. They don't match. And by the time I've predicted that a pedestrian is likely to cross the street, that's already too late. So what we present here is a contextual stack ensemble model. And that ensemble model starts with video streams. This is a video stream taken from a camera positioned in front of a vehicle. And it's taking images from the front of the vehicle. And this data is processed in various ways. So looking at the data, we're taking 32 frames, sequential frames from that video. These frames are annotated, so we have the bounding box. That bounding box indicates where the pedestrian is. And this is using a data set available, open access data set. It's called JAD, Joint Attention Understanding. From that, we take these 32 frames and we process them in 3 different pipelines. The first one is taking that pedestrian and representing the pedestrian in a skeleton. So these are the key points. We take that skeleton, we take the 2 points, and we see how these points move from one frame to another. So within 32 frames, we represent the movement of these key points with a graph neural network. And with these key points, we can then predict whether the pedestrian is likely to cross the street or not by just analyzing how the key points of that skeleton change over these 32 frames. That's the first pipeline. The reason we're interested in this pipeline, of course, it compresses the data by more than 4,000 times, and the model becomes much more simple and less complex. The other pipeline is looks at contextual data. So it looks at this bounding box and it decides whether it's at the road intersection, whether it is at the entrance of a garage, or what type of road, what's the traffic lights. And with that contextual information, we see again how it changes over time, and we feed it into a simple model, and that uses GRUs, gated recurrent unit network. The third pipeline just looks at the bounding box, looks at the size of the bounding box with respect to the frame, looks at how the size changes from first frame to the last frame. Is it increasing? Then the person is getting closer to the vehicle. Is it reducing? Then it's getting away from the vehicle. And whether it changes in terms of position within that frame. And then we can look at the journey of the pedestrian. So this is the data that we look at. By compiling this massive amount of data, which is these videos, through these pipelines, we've compressed the data significantly. And then the last bit is when we bring this together, and this is the SAP ensemble model, where we take the features produced by each of these pipelines, and we aggregate these features to then decide. And this is the CSC classifier, is the one that tells us, yes, the pedestrian will cross, no, the pedestrian will not cross. We'd like to say that you have 99.99%, but we don't. The accuracy is actually poor. But this is the best result. So our results got the best accuracy, the best F1 score, and a challenge ran in 2023 by the IEEE ITSS. And it was particularly trying to solve this problem, but using a different data set. Our model works the best on this data set, on the Pi data set, which was used for this model. What we're proud of is not that our results are better. It's that our results are much less complex. So you see here that we have less than 25 times complexity than the state-of-the-art models, which means that I have the time to take the data, model it in my digital twin, come up with a decision, and make an impact in the physical world with very low latency. And this is what's important. We're still not doing a very good job in terms of response score. 68 is not good, but we're getting there. We're getting there, and we need more data to improve this. But this is an example of how a digital twin can improve the safety of pedestrians, can improve the coexistence of autonomous vehicles, active travelers, normal cars put together, and then have more people do active travel instead of driving. Another example I'll talk about, again, about active travel, which is what I work on. It's about cyclist safety. I see there are lots of cycles around here, bicycles, but it's also raining, so I don't know how often people cycle in the road. In London, we tend to cycle a lot, but when we cycle, we're competing with buses, we're competing with vehicles, we're competing with pedestrians. I cycle, the last mile I cycled to the university when I go there, and I'm often in this situation where there's no separation between me and the buses and the trucks. I'm sometimes going too fast because I don't want to be stuck behind the bus. So I just cross the street even if it's straight, and I do that. And I know I shouldn't, but I do. 2 times I had an accident on my bicycle. It was a pedestrian that knocked me down because they don't see their phone, and it just think that they are the priority. Of course, they are priority, but they're putting me at risk as well. The other thing, the hidden challenge, is really air pollution. And air pollution is a major problem in London. And you sometimes feel it, sometimes you don't feel it, but it's there. And when you're stuck in traffic and you're inhaling that pollution, you just want to go faster and you want to get rid of it and you want to get to the point. So all of these are challenges. How can we model that? It's a very complex system. Again, of all the data that you want to raise. I mean, data is important, but that's not enough to model that. Can I, from that data, understand which route or which journey is at high risk? Can I make recommendations in real time to then change the behavior of cyclists and make recommendations on the longer run for improving how cycling lanes and how cycling policies can be designed? That's what we want to do. And the way we do it is we went and we collected data. We cycle all the time, me and my people in my research group, and we employed people to cycle in other routes that we don't usually cycle. So we have lots of data while you're cycling. The data we're collecting, we have a GoPro device in front of our bicycle, and we have a GPS. We have the acceleration, and we have the gyroscope, and that's the data that we're collecting. And then we use OpenStreetMap to get the features of the roads where we're cycling. Is it a major road? Is it a small street? Is there a cycling lane? Is there no cycling lane? All of that information is available on OpenStreetMap. And then we did crowdsourcing to get the labels. So we asked people who cycle in this area to tell us how safe they feel by just showing them a photo taken from our GoPro device in front of the bus. So that's the first bit that we did, getting that data. From that data, we then used our generative AI friends. We tried all of them. We tried ChatGPT, we tried Grok, we tried Gemini, we tried Claude. Grok gave us the best results. And what we wanted was to ask that LLM with some prompt engineering to tell us, can you describe the traffic that you see in that photo? And can you tell us how safe you feel cycling down that road? And why? And it will give us this kind of explainability of what kind of safety it will perceive there. And then we did some modeling in our digital twin environments to understand that. We wanted to model how safe a certain road is by looking at this data. We wanted to model the causality, what makes a road safe or not safe. And we wanted to come up with insights from that. So the way we did it is we've created this website. So if you look at this QR code, you can go to the website. And this is where we use that website to crowdsource the labeling. Whenever you, I think I can show it here. Let me see if that works. It shows on my screen, but not on your screen. Just give me a sec. Let me see. That's not what I wanted to show. In any case, you can check it later if you want. So what we have here is we have a website. In that website, we've uploaded all the data that we have. The colors that you see here are the positions of the GPS positions of the photos that are taken while we're cycling on both sides of the roads. The color itself tells you the perception of safety by the different people. And this is for each of these photos, we had at least 5 people to label them. Some of them have up to 10 people that were labeled. And they will tell us what they think about it, whether it's safe or not safe. Okay, so that's you, that's not me. I thought it was me. No, that's right. So we did that for the crowdsourcing, and we then looked at trying to predict the safety. Again, not 99.9%. It's very important. At best, it's 72. That's the precision that we have. The F1 score at best is 72. And we looked at the explainability, which is what we were interested in. And we found that you can predict the safety score anywhere in the world. If I just look at the photo, and you have photos of anywhere along the planet, right? If you go to Google Maps, you can find photos anywhere on this planet. And if you use that algorithm, it will tell you, it will spit out a safety score. It tells you that's how safe this space is to a cyclist. It might be right, it might be wrong. It's not very accurate. But again, that's the best out there. And it tells you what's more important. It tells you that what makes people safe is to have a separation between the cycling lane and the vehicles. You would have thought that, right? But that's confirming it. If not, then just to have a cycling lane without a separation is still better than a cycling lane. So you think that we solved the problem. We know how safe any place in London is. We can go back to municipalities and tell them we need to have cycling lanes everywhere, put a separation, and everybody will feel safe, and then everybody will cycle and everybody will be happy. But that's not it. It's not just that. There's more to it. We see that the third and the fourth important factors are the acceleration and speed. That's us cyclists. That's our behavior that is affecting our cycling safety. So our behavior is important, and that needs to be captured. We looked into it into more details, and you see that when we feel more safe, we tend to speed. This is in general, all the cyclists. This road stretch here, this is Mile End Road. Our university is just here. That's the one. This is called Whitechapel. Along this area, on this side of the road, on the northern side of the road, there's an outdoor market. And when we cycle here, you are stuck behind buses and there are vans bringing all kinds of goods to unload along this road. What I'm showing here, the black circles is where people accelerate. The red circles is where accidents have happened since 2000. And you will see where we tend to accelerate often correlates with the location of accidents. In this case here, I accelerate all the time because I'm sick of being stuck behind buses and whatever, and I just want to cut this. This is the worst nightmare of any cyclist, and I just want to finish this because I'm always, I know that I'm breathing all kinds of pollution in this environment. So we accelerate and we put ourselves at risk. In these areas, we feel very safe, and again, we accelerate, and this is why at intersections, we might have accidents. The point that I want to make is cyclist safety is not just determined by the road infrastructure, it's also determined by the behavior of cyclists. And you need to model all of that. And the only way to model all of that is in a digital twin environment, where you take the data, but you also model the behavior of cyclists. And that's very difficult to do. What we want to be able to do is, with that digital twin, we want to change the physical world. We want to first, on the long run, inform authorities what kind of road furniture, what kind of road design to implement the roads in order to make cycling more safe. And we want to influence policies. Maybe we want to limit the speed of cycling. Nobody likes this idea. I like it a lot. I wish we could do that, but nobody likes this idea. But that might be a way to easily improve the safety. We don't want to just change the long-term strategy. We want to have a real-time influence of how people cycle. If I'm cycling down this road and I'm listening to my Google map telling me to go left, right, or down, and it tells me 3 accidents happened here yesterday. Even if I'm inclined to speed, I might just reconsider that and go more slowly. I might decide to take a longer route because my map is telling me that the risk of pollution is much lower in this other route. So I might waste another 10 minutes, 15 minutes of my day, 30 minutes of my day, but I'm really improving my chances. So that's something that we can't solve today. We need to have that digital twin approach to modeling this thing. We started a new project this month, and in addition to the GoPro, we're also collecting air quality data. So the cyclists will be carrying their air quality data, the GPS and the GoPro, and we'll be going through that. And they will also be carrying smartwatches to measure the breathing rates and the heartbeats. So we want to see how when we're in a cardio rhythm, we inhale deeper and we inhale more. And when the pollution is very bad, that affects us more deeply. So we'd like to model that complex system. And this is where our digital twin will develop into a more meaningful a twin that can make these intelligent decisions. So why do I need the digital twin? Really, it is a complex system that no one model can do. It can't be modeled in one equation. Having access to a lot of data is not a model. To have that model, we need to bring all of these components together. And it's still not possible to capture everything that we'd like to capture. The challenges are many. Some of them are technical and some of them are non-technical. How do I connect all of these IoT devices? How do I manage the data generated by these devices? How do I control the CO2 footprint? Are technical challenges that we still don't have an answer for. We have more than 15 billion IoT devices. All of these are connected almost everywhere, and they're generating massive amount of data. I can't even pronounce this number, but it's almost 80 zettabytes of data. Now that data, most of it is redundant, most of it is garbage. This data is generated with these different IoT devices. It consumes energy to produce. It needs to be communicated from the edge to the servers. That takes bandwidth. From the service, it needs to go to the cloud. It needs storage. All of that is consuming. And the thing is that most of this data is garbage. Most of it is garbage. When we were looking at the pedestrian intents, we were able to reduce the data by more than 4,000 times. The same thing with the cyclist safety. I don't need all the image. Just ask Grok to summarize that image with 5 keywords, and that's sufficient. Just these 5 keywords can inform the model of the safety of cyclists. So a lot of this data is garbage. And this is where the edge intelligence is needed to avoid taking the garbage from the edge to the cloud. Can I get rid of the garbage at the edge? And that's very important. Of course, all of this consumes energy, and what really consumes a lot of energy is the data storage and the AI model. To train an LLM model generates more CO2 than 5 cars during their lifetime to train one AI model. So that's massive. I mean, the ICT sector emits as much greenhouse gases than the aviation sector. All of these are difficult challenges, but we think with technical challenges, we as engineers, as data scientists, we can tackle these challenges. We just need more time, we just need more data, we need more compute power to solve it. The more difficult one is the non-technical challenges, and perhaps fake sustainability is somewhere in between. Fake sustainability is what I call solutions or problems like COVID, where the emissions from road traffic, from aviation sector dropped significantly. That's great. They had the best air quality ever during COVID. But we were locked in. Nobody was in Piccadilly Circus. Nobody was crying. It was bad for the economy. It was bad for our well-being. It was bad for various people who depended on work to survive day by day. So that's fake sustainability. And to avoid these fake solutions, we need to model the complex system, and a digital twin is the way to do it. The other non-technical challenges are convincing people that the solution is good. I mean, in the UK, we have a system that we call ULEZ. This is the ultra low emission zones. What that means is there are some areas, some zones in London, where if you drive in with a vehicle which is not compliant with ULEZ emissions, then you get to pay a penalty. And people hate that. I know that people hate it. They hate it because they think it's going to limit their freedom and so on and so forth. The technical solution is perfect, but the solution is not accepted by the people. So it's useless. Either you're going to force people to take it, and that's no good because it will always create a backlash, or you need to convince people and engage them in that solution. Same thing, if you remember during COVID, people were attacking 5G antennas because they said that 5G is what caused COVID. That's not true. 5G did not do COVID, but this is what people were doing. They were attacking antennas. People think that climate change is fake news. Low traffic neighborhoods is another solution that we had, where we wanted to limit traffic in some areas, particularly around schools and residential areas, to improve the air quality. I can show you data that low traffic neighborhoods and ULEZ improved the attainment of students in school. It improved their marks in school. They did better with the exams during that time when there was low traffic neighborhoods and in areas of ULEZ. There are evidence there to show you that, but still people don't think it. So the non-technical challenge that I'm talking about here is that the technology that is not accepted will simply use this. And to have a technology accepted by the people, we need to have the public engagement from day one. And a digital twin is a good way to do that. Why is that? Because you can model the complex system. You can give it to people and say, this is what it looks like. This is what it looks like. This is your future. Check it, see it, interact with it, change this component and see what happens. You engage people with that, you engage them with the decision. And that's when you can make a difference. So with that, we started our research lab. We call it the Digital Twins for Sustainable Development Goals. And it's very much based on modeling that complex system and having actionable insights to help us make decisions for a better future. Our lab is led by social science. It is shaped by domain experts, transportation experts, energy experts, urban planning experts. And then we throw technology at the problem to solve it. Because we often want to throw technology at the problem before knowing what it is, hoping that it's going to do something good. So we do it the other way around. And just because you're interested in digital twins, these are some of the initiatives in the UK that are leading digital twins. So I was telling you about that paper. So this was by the DTNet Plus, which is this initiative here. The National Digital Twin Program in the UK, this is trying to bring critical infrastructure together and twin that critical infrastructure. The Gemini papers talk about the principles of digital twinning, and the Catapult is again, it's a weekly talk and seminar, and it brings together different initiatives on digital twinning. And just to say that this is not my work, this is a team's work. So all of those people are involved in the research lab. And that's my last slide. Thank you very much. Love to answer your questions if you have any.
Great talk. Just one of the things that I had in mind that you have the cameras attached to identify the dangers or pedestrian crossing. So in reference to like this would be collecting personal data. Like again, I know you have a Data Protection Act and you have GDPR. So do you need special permissions for collecting this? Because there is biometric data being collected.
So this data, we didn't collect it ourselves. This is an open source data set. That's the JAL data set. And it was collected in the US. I can't remember which state exactly.
California, I think so.
I don't think this is in California. I don't think so. California is this other one. I don't think this one is in California. Now, the data that we collected is this one.
Yeah, this one.
We didn't get an ethical approval for that data.
Okay.
And that's because we said, well, we're outdoor. We're not trying to identify anyone. Even if I know the face of the person, I don't know who they are. I'm just outdoor in the streets. It's as if you're walking and you're taking photos and someone happens to be in the background of that photo, right? So if you're just anywhere in an urban environment, you don't need to get authorization for that.
Right.
So from that point of view, we did it. However, with the new project that we're doing now, we needed to get ethical approval.
With GDPR, we need to, so for, that's different in Ireland, like with GDPR, we need ethical approval because the people, normal public is there. So I think the DP would be slightly different.
But we also have GDPR in the UK, but it depends on the data, right? So GDPR is when you can identify a person, then you need to get the authentication, the authorization of this person to use their data. But when you're out anywhere, you're a tourist, you're in a city and you take photos, you don't go ask every person in the background of the photo if they're okay for you to take a photo, right? And that's what we did. We've got the camera in front of our bicycle, we're cycling in the city. We don't know who the people around us are, just taking photos from that camera. So from that point of view, it doesn't need authorization from the people.
It's similar to meta glasses.
Mm-hmm.
Yeah.
I'm not sure. I mean, I've been involved in a few data sets, and we've had to either anonymize, which is definitely I know as an industry, we have to have big signs on the side of our vehicle saying, if you want your data removed, ring this number and we'll remove your data from what we're capturing. And then some other data sets we guys in Galway, where it would just be, but we just sign disclaimers that the people didn't mind being recorded. What we're double checking. But again, it can be slightly different rules. I think the UK hasn't adopted the full GDPR
No,
kind of,
it's-
or
like
implements
post-Brexit.
into law and stuff, yeah.
It's post-Brexit, you're not liable for GDPR until, that's what I know. And the Data Protection Act is more flexible than GDPR, as far as I know.
So I'm just going to show you what the photos look like.
Yeah.
So this is one example, right? Now, if I zoom in, I might know who this person is, but I wouldn't go and ask.
You're showing us the ChatGPT you generated. So,
Oh, am I? Why is that? So on Teams, it looks fine, but not here. What do I do then? How if I?
Maybe you stop sharing and then you
I know,
share this.
I did. So when you see on Teams, it's
Yeah,
there.
it's coming here on Teams.
Uh,
Yeah, now it's it. Yeah.
okay, that's
Yeah.
it. So yeah, I mean, if I click here, so this is what you see, right?
Yeah.
In some places you will see, it's possible that you see a person. We haven't seen any person there. Let me see, probably here you see people.
I know, for example, we have to blur or you generate alter the number plates of cars.
Yeah.
Because particularly if that asset is made public, or any information is made public, somebody could be, the theory is always, well, my husband is cheating on me and I could go, and then I just realised because I'm
Yeah.
thinking through the data set and I'm like, what was he doing in Shannon at this time? And oh, he's with his mistress. So,
Yeah,
you know,
yeah,
something like that.
Yeah.
Maybe that's fanciful, but you put in the theory of
Yeah.
the chances of actually happening are so slim, but that's the things we do. But
Yeah.
like let's say, I think
Indirect cases actually in the past, and that's why they went on to go in to anonymize, you know, these
I
things.
said, no, that is me.
Yeah, I mean, you know, that's a very valid point, because now we do have the ethical approval to collect similar data, but we're not asked to put a sign on the bicycle to say that we're collecting data. As we saw, I mean, I'm just looking at these photos and I don't, well, maybe here we can tell who the person is if I zoom in, but most of them, they don't have people's faces as such.
No. I'm like,
Well, then you can tell this person, for example, yeah.
I think
Yeah, it's interesting, you know.
like one of my PhD students wrote a paper and he's got samples from a data that we used a lot. And I could recognize the person straight away in the data. I know who it was. I worked with them for like 5 years. So I know who it was, even though it's all blur. And I'm like, yeah, that's I know.
And that's even if
Yeah.
you're rich, you know.
Yeah.
Because if you're able,
You
even
can be
if,
quiet about
yeah,
it, yeah.
even if something is anonymized, but you're able to identify that, again, it's still a GDPR.
Then it's not anonymous, then
Yeah.
yes. And no, you're right, yeah. I mean, as I said, we do have the ethical approval for this one. We haven't started the data collection and we were not asked to do that. I don't know if it will be different here. I mean, truly, if you just go down to the castle and you wanted to take a photo, you would do that, right?
Yeah.
So this is just taking many photos.
Yeah, I know, exactly. I think it's the purpose of the data gathering. Fine.
Yeah, yeah.
Yeah. You showed a model or framework at some point which had the camera, the OpenStreetMap.
Yes.
Get into graph and stuff like that.
Yeah.
And one thing. Like, graph is a huge general purpose model.
Yes.
And I'm wondering if there's kind of an abstract feature such as something like traffic density tells you that I mean that could be what Glock is finding as well. Just it might be saying, oh, okay, it's that, and then I'm using that. But the main thing is, are you giving all the information on the left hand side to Glock?
No.
Or is it just the image?
No, we're just using the image and you're asking Grok to come up to describe that image to us.
Okay.
To say, well, you know, there's a lot of traffic, there's a construction site, there's a cycling lane,
Yeah.
there's
Okay.
separation.
Yeah.
And we first asked, we've tried so many things with this project. And the one that works best is when we said these are the features that we're interested in. So instead of asking Rock to do anything, any kind of description, we said these are some of the features that we're interested in.
Yeah.
If there's a construction site, if it's a highway, if it's a high traffic density, so on and so forth. So we
You
did.
give all of those, every image, you give all of those features in there, in features.
So we asked Grok to tell us which of a list of predefined features it can find in this image.
Okay,
That's how we did it at the end. And that gave us the best results, which is still not very good. I mean, that's not the good results.
yeah,
Um,
like you say, not 99.9.
no. In real life, it's never like that.
Yes,
But this is not, I mean, I can't go to the authorities and tell them, go and invest this amount of money because my model is telling you that, because it doesn't give that confidence yet. But we think we can improve it.
yeah, so there's some interesting, so I've read PhD student doing a lot of work with VQA models. So he's focusing on small models, but he also kind of benchmarks with some large models. So I don't know if he's looked at Grok, particularly, but he's used that ChatGPT as well. And there's some things they do extremely bad,
Oh, yeah,
such as telling left from right.
yes,
So he asked the question, is the pedestrian facing left or right? And does no better than random chance. And those are kind of really important aspects of driving. If you're talking about pedestrian prediction, I know you're not using this method for predicting the pedestrian, but knowing if the pedestrian is facing left or right is extremely important if you're
absolutely.
and that's fundamentally how transforming the build is, the way the image is tokenized, you lose that information. But it seems that could explain that a lot of that 0.7, firstly,
Yeah.
the 99% that you might want to get,
I mean, we looked into that, and we think that the way we did the labeling was not very correct. Or maybe not correct, but it came up with noisy labels. So where we looked at every single image where it was misclassified, and it's more often than not, it's misclassified when you have different people labeling the same image, and one of them gives it a 4, the other one gives it a 6.
Yeah.
And it gets lost between this or that. So when you want to convert this, not continuous, but a range of values, we had 10 classes, and you wanted to bring that down to just safe or unsafe, then you get lost between the 4, 5, and 6. And when it's half here, half there, it's just, it loses it completely. And what we want to do next is try to avoid that. So we want to have 4 classes instead of 10 classes. And with that, hopefully, we will do a better job. So this is one of the reasons. The other reason is the people who cycle are not the ones who labeled. So we cycled, we collected the data, we uploaded all of that data into this website, and then we recruited people that we don't know through a platform. And we said, these people, they cycle, and we saw them, and we said, can you label those for us? We don't know anything about them. And I don't think that worked. We thought it was going to be a good idea because it's going to kind of anonymize and not be biased to anything. But it ended up giving us conflicting results. So what we will do this time is we're going to have the same person cycle for 30 minutes, and then we ask them to watch that video again and label every frame themselves. And that becomes, I think, more correct, less generalizable, but more correct. But that's a start, I suppose. But yeah, I mean, LLMs, the potential is really very, very nice, very scary as well, because you just don't know what you're going to get with these LLMs. But at the same time, the potential is great.
Four times reduced.
Oh, yeah.
But the errors can be unpredictable.
Yes, true. I mean, we asked Grok to label all of these images, and it's not less consistent than the human labelers. It's not the same, it doesn't match. But if you look at the distribution of the labels of Grok, it's not worse than our labelers. So, yeah. Anything else? One. Thank you very much. Thanks a lot. So let's see, what do we do here? In stop recording.